All right, chemist, this is Ralston Valley High School Chemistry's AP Chemistry Lecture Series, Chapter 12 on kinetics. We are going to be discussing today the integrated rate law and half-lives. Let's go ahead and get started. All right, so picking up where we left off after our last discussion of the differential rate law, we're now going to be looking at another way of expressing rates of reaction, this time with what we refer to as the integrated rate laws. Recall from our last set of slides, the differential rate law described the rate of reaction as a function of the concentration of one of the reactants present in the system. In this case, with the integrated rate law, rather than looking at rate of reaction as a function of concentration, now we're going to be looking at rate of reaction as a function of time since the reaction began. The integrated rate law can be derived from a differential rate law. So that is to say, if you know the differential rate law, you can use that to find the integrated, or vice versa, you could use the integrated rate law as a tool to help you find the differential rate law for a particular reaction. This is going to involve a little tiny bit of calculus right here, which we're going to move through fairly quickly. Recall again, for the actual AP test, you are not responsible for deriving this law. I'm just going to go through real quick here and do the integration for those of you who are currently hanging out in a calculus class and might like to see where these rate laws relate to one another, mathematically speaking. So to begin with, let's go ahead and have a look at the rate law as defined by our differential rate law for a first-order reaction. That is to say, our rate of reaction is going to be equal to the change in concentration of some reactant species A with respect to time, and that rate of reaction is going to be equal to some constant K times A's concentration raised to the first power, since again this is a first-order reaction. And important to note here, folks, see here that I have actually made the change in concentration of species A. I've given a little negative sign out in front of that there because A is one of our reactants, and as such, it's going to be decreasing in concentration over time. So we've got our differential rate law. What we're now going to do is we're going to restate this with slightly different nomenclature here. Rather than looking at here the change in concentration of species A with respect to time, we're going to look at the incrementally small change in concentration of that species A with respect to time. For those of you who have spent some time in calculus land, we're going to define that here as a dA over dt is equal to minus K times the concentration of species A. So we're looking at an incremental change in concentration with respect to time. And also notice here, as I went from the first equation to the second, I also multiplied both sides of this equation by -1 to bring that negative sign over onto the right side of my equation. And from this spot now, I'm going to do a quick rearrangement of my equation to gather my variables on each side. First thing I'm going to go ahead and do is divide both sides of the equation by the concentration of species A. That's going to cancel this out on the right-hand side over here. And I'm also going to multiply both sides of my equation by dt, and that will cancel this out on the left side of my equation over here. And I can now rewrite this for what I've got as now 1 over the concentration of species A with respect to A, that is 1 over A dA, is equal to minus K dt. And at this point now I've gathered my variables, I'm okay to go ahead and do my integration. Now you may remember from your calculus land that the integral of 1 over A dA is going to give us the natural log of A. So my equation now becomes the natural log of A is equal to minus KT plus the constant C. And at this point we've got the generic form of our integrated rate law for this particular reaction. Now it's worthwhile to take a quick moment to think about what this constant C represents in our system. If you can imagine for a quick moment here, if we start off at the initial time of this reaction beginning, that is at t equals 0, the value of my part of my expression here, which is the minus kt, would become minus k times a time of 0, which means we can just ignore that entirely. And that implies, therefore, that the value of my constant C in this expression would be equal to the natural log of the concentration of species A at that initial time of time equals 0 for my reaction. So I'm going to go ahead and define then the constant C is equal to the natural log of, and we're going to go ahead and notate this as the concentration of A with a little knot down below there indicating under the initial conditions of the system at time equals 0. So my complete version of this integrated rate law then for a first order reaction is the natural log of the concentration of species A is equal to minus a constant K times T plus the natural log of the concentration of species A under the initial conditions of our system. And again, that value of K is the rate constant K, the same rate constant K which you were introduced to in our discussion of the differential rate law earlier in our unit. Now, do not panic right here if this math is beyond what you currently have seen in your math class right now. You're never going to be held responsible for doing any of this derivation of these equations in the course of the AP test. What you will be held responsible for is being able to use the outcome of this equation in order to be successful in the AP chemistry world. So don't worry about the derivation if this math looks new to you. We're going to do a couple more derivations similar to this in the next couple of slides, but we do want to be able to make use of this equation that we have now derived. Now, speaking of the equation we have just derived, something important to note here is this. That equation, the natural log of A's concentration is equal to minus KT plus the natural log of A's initial concentration, is in the format of a straight line graph. That is, this is essentially, even though it kind of looks messy, nothing more than just an equation which is in the format of slope-intercept, that is y equals mx plus b. In this particular instance, the y variable is going to be represented by the natural log of A's concentration. My slope would be equal to minus the rate constant K, and then the x variable in this equation is simply the time since the reaction began. And then last thing that we see here in my equation, the b value, which again represents the y-intercept, in this particular equation is going to be the natural log of A's initial concentration. Now this is going to be super useful for me here as an analytical tool because what that really means is then I could graph the natural log of the concentration of some species over time, and if I find that graph of natural log versus time, if it yields a straight line graph, that is definitive evidence that this particular reaction would be a first order reaction. So it's essentially a tool that allows me to determine reaction order from simply data of concentrations and time. And furthermore, beyond that, by looking at the slope of that line, you see here that my m value in my equation, that is the slope, is equal to minus the rate constant K. So if I take that graph of natural log of concentration versus time, and then I find the opposite of the slope, that allows me to solve directly for the value of the rate constant K from this data as well. And we'll see a similar process in the next couple of slides here as well. So that's it. First order reactions yield a straight line graph for the natural log of concentration versus time. All right, so here we are now, having derived the integrated rate law for a first order equation. We're now going to take a look at how to derive the integrated rate law for a second order reaction. And recall, for a second order reaction, our reaction rate is defined as some constant times the concentration of some species A raised to the second power. Now I'm going to go ahead and write just the same way we did last time. That rate of change in concentration of A with respect to time is equal to K times A's concentration squared. And we're going to make the same manipulation of this equation that we did last time. That is, the instantaneous rate of change, that is dA dt, is equal to a minus K times A's concentration squared. And all I've really done from this first equation to the second one is moved that negative over from the left side of the equation to the right side. And again, recall that that rate is a negative change in concentration because species A is one of the reactants, which should be going down in concentration over the course of our reaction. With this now, I'm going to go ahead and rearrange my equation by gathering the variables onto their appropriate sides. So I'm going to divide both sides of my equation by the concentration of A to the second power. I'm going to multiply both sides of my equation by the dt. And when I do that, I get my new expression, which is 1 over the concentration of A squared dA is equal to minus K dt. And now that I've got it in this setup, I can go ahead and integrate my equation. Now you may recall from your calculus class that we can go ahead and do our integration here. 1 over A's concentration squared is equal to A to the negative 2 power. So using your integration rules here, we know that this is equal to, therefore, negative A's concentration to the negative first power. And then on the right-hand side here, the integral of minus K dt would be minus KT plus some constant C.
Now, that being said, let's again think about what the constant really represents. If I plug in a time equal to 0 for my equation, that would give me then, at the initial set of conditions for a system, the initial concentration of A, or I guess minus the initial concentration of A to the negative first power, would be equal to my constant C. So we can therefore go ahead and just slightly rewrite this in a little bit different format here, but it's really the same thing we've just seen. That gives me 1 over A's concentration would be equal to kT plus 1 over the initial concentration of A. Now, importantly, folks, something I want to kind of look at here for a quick moment is what we see when we look at that particular equation. This equation is in the format of a straight line. That straight line essentially is a y equals mx plus b format. Now, in this particular instance, the y variable is really represented by my 1 over the concentration of A. M, in this case, would be the rate constant K, and X would be the time t since the reaction started. And then my B, my y-intercept in the system, would be 1 over the initial concentration of A. So long story short, for a second order rate law, the graph of 1 over A versus time should yield a straight line graph whose slope is therefore equal to the rate constant K. Now, this is a super useful thing for us to use now, because again, if I can find the slope of a graph of 1 over A versus time, and it is a straight line slope, that tells me two things. Number one, it tells me, in fact, this is a second order reaction. So graphing this would be one way of determining the order of reaction, graphically speaking, and the AP test will often ask you to do that. Alternatively, the other thing that tells me is if I can find the slope of that particular graph, that allows me to solve for the rate constant K for my reaction as well, which is another great tool we can use here. So again, we see a second order reaction here, 1 over A versus T, yielding a straight line graph. All right, we have one more go here now, this time with a zero order reaction. We're going to go through the same process we've seen in those last two slides. So for a zero order reaction, the rate of change of concentration of some reactant A with respect to time is equal to the rate constant times A's concentration to the 0 power, where any variable to the 0 power, if you recall, is 1. So that's another way of saying the rate of change of concentration with respect to time is a constant value. Now let's rewrite this in slightly different format here. The instantaneous rate of change of concentration of A with respect to T, that is dA over dt, would be equal to minus some constant K, and just like we saw before, really all I've done right there is bring the negative from the left side of the equation over to the right side, recognizing again that A is a reactant which should be decreasing in concentration over time. We'll go ahead and do the same thing we did before, that is gather our variables. I'm going to go ahead and move the dt to the right side of my equation, multiplying both sides by dt, yields now the expression dA is equal to minus k dt. And from here, this looks like we're now set up to solve for the integral of this equation right here. We'll take the integral of the dA gives me simply the concentration of A, and then again on the right-hand side, the integral of minus k dt would yield minus kt plus some constant c. And thinking logically about this the same way we did in the previous slides, if we insert a time equals 0 into this expression, that would be under the initial set of conditions for our system, the value of that constant c would simply be equal to A's concentration under the initial set of conditions. So this yields for me now the integrated rate law for our zero order reaction, which you'll see here is the concentration of A is equal to minus kT plus the initial concentration of species A. And just like we saw on those previous two slides, this particular equation is again in the format of a slope-intercept graph, that is y equals mx plus b for a straight line. And in this case, the value of my y variable, the dependent variable, is the concentration of A. The slope of my line would be minus the rate constant k, and then the x variable, yet again, is the time t. So long story short here, looking at this particular equation, if you graph the concentration of a species versus time and find that that graph yields a straight line graph with a negative slope, what that really tells me is I now have definitive evidence that I'm dealing with a zero order reaction. And again, furthermore, we can take this one step further. recognizing that I can find the slope of that concentration versus time graph, that slope would be equal to negative of the opposite value of the rate constant k. So putting it all together here, folks, we really have three different possible outcomes here. If we graph natural log of concentration versus time, that yields for us a straight line. That is definitive evidence of a first order reaction. If we graph 1 over the concentration of A with respect to time, and that graph yields a straight line, in that case we would have a second order relationship there. And in this case, as we saw on this slide, if we simply graphed concentration versus time, and that yields a straight line graph for me, that would be definitive evidence of a zero order reaction. And that's essentially how we use the integrated rate law. We're going to go ahead and graph each of those three different possible outcomes, natural log of concentration versus time, 1 over concentration versus time, and concentration versus time. And we're simply going to look for which of those three yields for us a straight line graph to determine our reaction order. The AP test questions tend to be literally that easy. It comes down to, can you recognize which of them is a straight line? They tend to be fairly friendly problems, even though the derivation of this equation was a little bit heavy on the math side of things. So let's go ahead and move forward here and see how we can use this information. One of the applications we can make of our integrated rate laws is to deal with the half-life of reactions. Now, you're familiar with half-life from our previous conversations around generally nuclear chemistry. In a more generic sense, really the half-life of a chemical reaction is defined as the amount of time required for a reactant species to reach half of its original concentration. And how we solve for half-life is going to depend for us on what the order of our reaction is. And we'll go ahead and work through a couple different possibilities here within these next couple of slides. Starting off to begin with here, let's think about a first-order reaction. Recall our integrated rate law for a first-order reaction was the natural log of the concentration of A was equal to minus k times the time t plus the natural log of A's initial concentration. And at this point, we're going to go ahead and do a little bit of manipulation of this equation here to help us solve for the half-life. I'm going to go ahead and start here by subtracting the natural log of A's concentration from both sides of this equation and adding the value kt to both sides of the equation. That rearrangement is now going to yield kt is equal to the natural log of A's initial concentration minus the natural log of A's concentration at some time in the future. Now, if you remember your log rules, recall that log A minus log B, as long as you have the same base, is equal to the log of A over B. And so I can go ahead and then apply that log rule, which would yield now the equation, kt is equal to the natural log of A's initial concentration divided by the natural log of A's current concentration. And by definition now, at the half-life time, by definition, the concentration of A is half of what it started with. So I can go ahead now and make a substitution here for the concentration of A at some time t, at specifically the half-life time t. That concentration would be equal to A's initial concentration divided by 2. Let's now take that defined value of A's concentration at the half-life time and plug it into our equation. That will now yield an expression which is k times the half-life time, since again we're defining specifically now at this half-life, is equal to the natural log of A's initial concentration divided by the natural log of A's initial concentration divided by 2. And you can see now I can make a quick cancellation right here and do a rearrangement of this equation. This simplifies down quite nicely to k times the half-life time is equal to the natural log of 2. Or another way of stating that is, if I rearrange one more time, the half-life time of a first-order reaction would simply be equal to the natural log of 2 divided by the rate constant k. You might see this sometimes expressed on the AP test as the actual numerical value of that natural log of 2 rounded to 3 decimal places, a value of 0.693 divided by the rate constant. Now, that being said, this tells me something really useful. One thing I see here is that half-life time does not depend upon, in any way, the initial concentration of species A. So if you have a set of data in which you see the half-life of the reaction does not change as time progresses, what that really means is you're probably looking at a first-order reaction. The other thing that's really nice here is that if I have the half-life, I can use that half-life then to solve for the actual value of the rate constant k. So this is a really useful tool. If I'm given a set of data, I can simply solve for rate constant k by looking and seeing where the value of the concentration of A has dropped to half of where I started, and then use that value in my equation to essentially plug in and solve for the value of my rate constant. So another super useful tool we can use in our repertoire. We'll go ahead and see now how that applies to a second order reaction on our next slide.
All right, so let's go ahead and have a look at our first example here for a half-life problem, this time involving a first-order reaction. In example 1, we're giving you information that says the half-life of a first-order reaction is 20.0 minutes. And we'd like you to calculate for us the value of the rate constant K for this reaction. And as a follow-up, how much time will pass before the reaction is 75% complete. Now, because we have been provided information here that this is in fact a first-order reaction, we have an equation which we can select to use here that defines the half-life of a first-order reaction as the value, the natural log of 2, divided by the rate constant K. And a simple rearrangement of that equation is going to solve then by multiplying both sides of the equation by K and then dividing by the half-life time T1 half. I get a new rearranged version of this equation that tells me the rate constant K of a first-order reaction would therefore be equal to the natural log of 2 divided by the time of 1 half-life. And if you look to what we were provided in this problem here, we were given information that the half-life of this first-order reaction is 20 minutes. And therefore, I can simply plug into my expression here, solving for the natural log of 2 divided by the half-life time of 20.0 minutes, yields, when I plug this into my calculator, a value of the rate constant K equal to 0.0347. And my units there I can see here are simply units of inverse minutes, since again we had the natural log of 2 over 20 minutes. The only unit showing up there is minutes in my denominator. All right, so I've got now a value of the rate constant K. Now that I've derived the value of that rate constant K, let me go ahead now and write the rate law for this reaction. The rate law of a first-order reaction is by definition equal to the rate constant K times the concentration of the reactant species A raised to the first power. Now, that being said, I could also define my rate law as the integrated rate law here, that is, the natural log of concentration of A is equal to minus kT plus the natural log of A's initial concentration. And using this integrated rate law, I'm now able to plug in some values that will allow me to solve for the amount of time that has passed when this reaction becomes 75% complete. So logically speaking, if the reaction is 75% complete, that would imply that 25% of the reactant species remains. And as such, I could then plug into my equation. The amount currently remaining would be 25%, or expressing that as a decimal would be 0.25. So the natural log of 0.25 would be equal to minus kT, which would be equal to minus my rate constant K we had just previously calculated as 0.0347 inverse minutes times the time t plus the natural log of A's initial concentration, which was essentially 100%, all of the species present initially, but expressing again that as a decimal value would be essentially 1. So I've got my expression now here. I can now solve for my missing variable t here. Simplifying mathematically using my calculator, the natural log of 0.25 yields a value of negative 1.386. That is equal to negative 0.0347 inverse minutes times t plus the natural log of 1, and again that natural log of 1, or the natural log of 1, is 0. And then dividing here by negative 0.0347 inverse minutes yields a time t of, not surprisingly here, 40.0 minutes, which should make perfect logical sense, given that if we have a reaction which is 75% complete, after one half-life it would be 50% complete. After the second half-life it should be half of the half remaining, which would then react, putting me then at 2 half-lives in, which, when logically speaking, would be 40 minutes. So this seems to then correlate nicely to the prediction we would make just using our logic. All right, so at this point we've now seen how you can use the half-life equation to solve for the rate constant K, and then using that rate constant k once it's been defined in the context of the integrated rate law to solve then for an amount of time which has gone past. We'll move on to our next slide.
All right, now for a second order reaction, we'll go ahead and see how we can do the similar manipulation as we did on the previous slide in order to derive an equation to express the half-life of this reaction. Recall the integrated rate law for my second order reaction is 1 over A's concentration is equal to KT plus 1 over A's initial concentration. And we're going to make the same manipulation as we did last time. That is, I recognize that at the half-life time, by definition, A's concentration is half of what it started as. So I can therefore substitute the initial concentration of A divided by 2 for the concentration of A in my integrated rate law expression. That now yields for me here a new expression, which is 1 over A's initial concentration divided by 2, there's my substitution, is equal to K times the time t, which at this point must be the half-life time, plus 1 over A's initial concentration. And yet again, we're going to go ahead and do a quick manipulation of this equation here. If I recognize I can bring the 2 up out of my denominator right there, this now yields an expression which is 2 divided by A's initial concentration. And then I'm going to subtract from both sides here 1 over A's initial concentration to bring that over to the other side. That now gives me 2 over A's initial concentration minus 1 over A's initial concentration is equal to K times the half-life time. And at that point, I can do a quick subtraction there. 2 over A naught minus 1 over A naught yields simply just 1 over A naught, and that therefore will be equal to K times the half-life time, T1 half. And a quick manipulation one more time here, I can rearrange and solve for T1 half. That gives me a half-life time is equal to 1 over the rate constant K times initial concentration of A. Now that being said, a very big difference here between this expression and the one we saw in the first order reaction. That is specifically, the half-life time of a second order reaction changes depending upon how big the value of A's initial concentration is. And if we think about the inverse relationship there, the larger the concentration of A initially, the smaller the value of the half-life time T1 half. And that's a really good tool that I have again in my repertoire. What that really means is then, I can look at successive half-lives as time goes by for a particular reaction. And if I see the larger the value of A's concentration, the smaller the half-life time, that is, if my initial half-lives are shorter than they become later on, that's a really good indication that the type of reaction I'm seeing is going to be a second-order reaction. That is unique to second-order reactions we see this property. So again, first-order reactions have a constant half-life. They do not change depending upon what A's initial concentration is. For a second-order reaction, the half-life time is smaller the larger the value of A's initial concentration, and that applies essentially the half-life time gets bigger and bigger and bigger the longer the reaction goes on. All right, now that we've derived expressions for the half-life of both a first-order and second-order reaction, let's now have a look at a half-life of a zero-order reaction. Following the same process we went through before, the integrated rate law for a zero-order reaction is the concentration of species A is equal to minus the rate constant K times time t plus the initial concentration of A. And we're going to make the same substitution we did before. That is, by definition, at the time of one half-life, A's concentration is half of what it started as. I'm therefore going to plug in A naught over 2 for the concentration of A into that integrated rate law expression. And as I do so, I get a new expression here now, which is concentration of A under initial conditions divided by 2 is equal to minus K times the half-life time T1 half plus A's initial concentration. And we'll go ahead and do a quick manipulation here. We will start off here by subtracting from both sides A naught over 2, and I'll add to both sides the value K times T1 half. And upon making that manipulation, my new expression here yields K times T1 half is equal to the concentration of A initially divided by 2. Or again, I could rearrange and solve here. That is to say, the half-life time T1 half is equal to A's initial concentration divided by 2 times the rate constant K. Yet again here, we see that the half-life time now is dependent upon A's initial concentration. And so for a zero-order reaction, That zero order reaction, again, is going to change half-life depending upon how much of the stuff we have present in our system. But this time, the larger the concentration of A, the longer the half-life time is. That is, for this particular relationship, we have a direct relationship between half-life time and A's concentration. Oftentimes, these zero-order reactions occur when we have a solid-state catalyst required for the process to occur. And we can think for a moment about a particle scale reason why this might actually be the case. Imagine for a moment here that I've got some sort of solid-state catalyst, and then I've got a gas phase reactant present here that is reacting over time. If you think about it for a quick moment here, once the surface of that solid-state catalyst is completely covered up by the reactant species A in the system, at that point, no matter how much I change the concentration of species A, no more of that species can come into contact with the surface of the catalyst, and therefore, the rate of reaction would be essentially independent of the concentration of species A. That is to say, this is a zero-order reaction. Now, logically speaking then, the more stuff which is present in the system, the longer it would take at a constant rate to work through that reactant until half of it had been consumed. So that is to say, the half-life time is going to be longer depending upon how concentrated species A is under the initial conditions. If you had a very, very small concentration of species A, then it's not going to take very much time to work through the amount of material which is present in your system to have it be consumed, which means, therefore, at low concentrations, you would expect to see a relatively short half-life. So, long story short, if you find that the half-life time decreases as a reaction proceeds, that's a pretty good indication that you're looking probably at a zero-order reaction for that system.
All right, continuing here with a second example half-life problem right here. In this particular example, we're going to be examining a system in which we have molecules of the organic molecule 2-butyne, which undergo a dimerization reaction, di meaning two, so a dimerization reaction is a reaction in which two individual species react together to form one product. And so in this dimerization reaction, we're going to be taking two molecules of the 2-butyne, combining them together to form the species C8H12. We've given you an equation up at the top right there describing this reaction. And we're going to ask you to use the data in the supplied data table to determine the half-life of 2-butyne. Now, have a look for me at the data table here that I provided you. In this data table, we have information provided about the time since the reaction began and the concentration of the species 2-butyne, that is the C4H6. Now, interestingly enough here, folks, we noticed from our previous conversations that we can use a graphical method of recognizing the order of reaction in terms of determining which graph yields a straight line relationship. That is the concentration versus time, the inverse of concentration versus time, or the natural log of concentration versus time graph. So what I'm going to do here is I'm going to use a spreadsheet program here, Google Sheets or Excel or something like that, in order to use the data provided to make a couple of different new calculations here. Starting off, I'm going to go ahead and find the natural log of the concentrations which were provided to me in column B. So using my spreadsheet program, I can go ahead and solve for the natural log of each of those concentrations. And then in my fourth column here, we're going to call this column D, I'm going to calculate the inverse of the concentration of the species at each of those different given times provided to me in the data table. And now that I have each of these data sets provided, I can now use my spreadsheet program to generate some graphs. The first graph we're going to look at here is a concentration versus time graph. So we'll go ahead and plot that graph here, and you'll see here we've got a kind of nice downward sloping curve in the concentration versus time. I'm then going to plot the natural log of concentration versus time graph, and yet again you'll notice here with my second graph plotted, I yet again have a nice curve forming here. And then for the third graph, I'm going to produce here the inverse of the concentration of the 2-butyne versus time. And by plotting that inverse of concentration versus time graph, you'll see here that I have a very nice visually direct linear relationship between those two variables. And this now provides me enough information to determine the order of reaction. So looking at the first graph there, the concentration versus time yielding a non-straight graph essentially eliminates the possibility of a zero-order reaction. The second graph there, the natural log of concentration versus time graph, would have been a straight line had this been a first-order reaction, but again, since there's a curve there, that implies again this is not a first-order reaction. The inverse of concentration versus time graph yielding a straight line graph there provides me justification that in fact this is a second order reaction, as we had derived on our previous slide that a inverse of concentration versus time graph should be a linear relationship in that y equals mx plus b format in our previous slide. So long story short, I'm going to go ahead and justify here that because the inverse of concentration versus time graph is a straight line relationship, this is therefore a second order reaction. And because this is a second order reaction, I can then use that to now write the integrated rate law of this particular reaction. For a second order reaction, recall that the inverse of the concentration of species A at some given time is equal to the rate constant K times the time t plus 1 over A's initial concentration. And again, recognizing from our previous conversation, this is essentially a straight line graph in the format of y equals mx plus b. You'll notice here the slope of that graph, that is m in this expression, really is taking the place here of the rate constant k. So for this reaction, the slope of the graph should yield for me the rate constant k. And you'll notice here that I've actually used my spreadsheet program to find the best fit line here, the equation for the best fit line of 1 over concentration of C4H6 equals 0.0612x plus 99.4. So my slope there of 0.0612 is therefore the magnitude of my rate constant k. Now, that being said, once I have found that information here, I've got to do a little bit of thinking now about the actual units that are going to be present for that rate constant k. Recall that for a second order reaction, the differential rate law of a second order reaction would be rate is equal to k times A's concentration squared. And I could then rearrange that equation to solve for the rate constant k. That would give me the value of the rate constant k is equal to the rate of reaction divided by A's concentration squared. And let's then use this to analyze the units. A rate of reaction, by definition, is defined in the units of moles per liter per second, or molarity per second. And then in my denominator, I've got the concentration of A squared, which would be units of molarity squared. So simplifying this expression then, the molarity would cancel out with the square in the denominator, and I can get rid of it in the numerator. I get a new expression, which would therefore be inverse seconds in the numerator divided by molarity in the denominator. And then a quick rearrangement to make these units make a little bit more sense. That would therefore yield units of liters per, in my denominator, moles times seconds. So I can now define here my rate constant K as 0.0612 liters per mole seconds as the rate constant. And now that I've determined that rate constant, I can now go about solving for my half-life. Recall from the previous conversation we had on the previous slide, the half-life of a second order reaction is equal to 1 over the rate constant K times A's initial concentration. And I can therefore go ahead and start plugging in some values here. I would get for this value then the half-life time equal to 1 divided by the rate constant K we just solved for of 0.0612 liters per mole seconds times the initial concentration of A in this system, which I can then just go back and look and find off of my data table. We started off at the initial concentration of the species C4H6 at a concentration of 0.01000 moles per liter. And plugging those values into my half-life expression, I then get a value of, when I type into my calculator here, 1,634 seconds, which looks like 3 sig figs given from our values we've derived thus far, would be 1,630 seconds for my half-life time. And again, notice here that those units happily cancel out in my denominator. The liters cancel with the liters, the moles cancel with the moles, and I get units of 1 over seconds, or otherwise just known as seconds. So long story short, we can get a lot of information by a simple graphical representation of those three different relationships: concentration versus time, natural log of concentration versus time, and inverse of concentration versus time. On the AP test, they're unlikely to actually ask you to derive each of those column values because they don't want you spending all your time making mathematical calculations. What they're more likely to do is just to provide you with those three graphs, and those problems at that point become very, very easy. It literally becomes, can you recognize which of these things is a straight line? And as long as you remember that concentration versus time being a straight line graph will yield a zero order reaction, natural log of concentration versus time is a first order reaction, and inverse of concentration versus time is a second order reaction, you should be then good to go and get those problems on a free response question for the AP test. All right, that's it for our second example. We just have a little bit to wrap up on our two final slides. All right, what we have on this slide here is a summary of the information we've provided you on the previous slides here, so you have one handy place to kind of refer back to as you start working some example problems. The key idea is that if we have information about the concentration of a reactant versus time, we can determine the reaction order by a variety of different ways, one of which is the relationship of our graph that yields a straight line relationship. So have a look here for me first of all. The first row I've given you here is the generic rate law, or the differential rate law, we would say. For a zero order reaction, the rate of reaction is itself a constant value. That is, it does not depend upon the concentration of any species. The first order reaction has a reaction rate which is dependent upon the concentration raised to the first power. And the second order of reaction would yield a rate law expression of the rate equals to the rate constant K times the concentration of the species raised to the second power. So our zero first and second order reactions. We then have the corresponding integrated rate laws down below. Recall for our zero order reaction, we derived an equation which was the concentration of species A was equal to minus the rate constant K times T plus A's initial concentration. And again, we recognize that that was in the format of a y equals mx plus b expression, meaning therefore the concentration versus time graph there should itself be a straight line, where the slope of that straight line is equal to minus the rate constant K. For our first order reaction, we derived the expression the natural log of concentration is equal to minus the rate constant K times the time plus the natural log of A's initial concentration. And yet again, we recognize that is a y equals mx plus b straight line expression, where the y value is the natural log of A's concentration, the x value is the time t, and the slope of that line is minus the rate constant K. So again, we would have a straight line graph for the natural log of concentration versus time, where the slope is minus K. And then last, our second order reaction had the format in the integrated rate law of 1 over A's initial concentration is equal to KT plus 1 over A's initial concentration. In this particular instance, yet again, we have a straight line equation, y equals mx plus b. This time, however, the straight line graph would be a 1 over concentration versus time plot, and the slope of that graph would have the value of the rate constant K. So again, as long as we can recognize which was a straight line, we can determine that reaction order. And then last but not least, down below there, we have the half-life equations for you. For the zero order reaction, the half-life time is equal to A's initial concentration divided by 2 times the rate constant K. For the first order reaction, the half-life was equal to 0.693 divided by K. And for the second order reaction, the half-life time T was 1 over the rate constant K times A's initial concentration. Now, important to note about those half-lives again here, folks. Notice, please, the only half-life which is independent of concentration is the half-life of a first-order reaction. So if you are provided data in a free response question that shows you that the half-life does not change depending upon the concentration of the species, that is sufficient justification to prove that you are dealing with, in that case, a first-order reaction. Whereas for that zero-order reaction, again, if you have a higher concentration, that is A naught is initially larger, your corresponding half-life time would be larger. Or for a second order reaction, if the initial concentration is larger because that A naught is in the denominator, that would imply second order reactions would therefore have a shorter half-life as the concentration increases. All right, so as you work those problems, just kind of keep these in mind. Of the very few things you have to straight up memorize for the actual AP chemistry test, knowing which of these graphs is itself a straight line relationship is a very, very valuable thing to have. Sometimes can make or break a free response question for you. So I would commit to memory here which of these represents the plot of a straight line graph for a 0, first, and second order reaction. All right, one final note of interest here as we finish up our conversation around rates of reaction here. Let's talk for a moment about catalysis. As you have seen in the past, a chemical reaction can be sped up by the addition of a species we call a catalyst, that is, a species which increases the reaction rate by essentially providing a pathway of decreased activation energy. And again, recall a catalyst itself is not consumed during the course of that chemical reaction. In particular, there's a couple different types of catalysts you might come across. The first is what we refer to as a homogeneous catalyst. That is a catalyst which is present in the same phase of matter as the reactant molecules. And that is in contrast to what we refer to then as a heterogeneous catalyst. That is a catalyst which has a different phase from the reactant species present. And usually that heterogeneous catalyst in most times is going to be for us a solid. So have a look first of all for me up at the top here, in which we've provided you an energy profile diagram. This energy profile diagram may be familiar to you from our work in thermodynamics in chapters 6 and 16. So have a look at the first pathway here, where we start off with the energy level of our reactants, labeled here on your graph as the energy level B. And you'll see as this reaction proceeds, the energy of the system goes up until we reach a maximum. We called again that point of the maximum there, the point of the activated complex. And then from that position down there, we then drop down to a lower overall energy level at point A, down at the bottom right there. So we see this reaction overall saw a decrease in the energy of the system. That is to say, it was an exothermic chemical reaction. Now, I could increase the rate of reaction were I to provide an alternate pathway by which this reaction could proceed. And the logic behind this is essentially kind of similar to thinking about like two soccer players playing soccer across a hill. If I had a soccer player starting up here at the potential energy level B, the soccer player could be kicking the ball upwards towards the hill. If the ball is kicked with sufficient energy, it would have enough energy to get up and over that hill, and then from that position, it would then continue on spontaneously towards the product side there where the other soccer player is waiting. So we see there that a couple things might affect the rate at which that reaction occurs. One thing is the soccer player could just kick the ball harder. Harder kicks means essentially there's more energy in the system. This would be kind of akin to a system where there's a higher temperature, more energy available. And logically speaking, at a higher temperature, most chemical reactions run faster because more of those kicks would get the soccer ball up and over the hill. Which is why we put your food in the refrigerator to cool it down and therefore slow down the rate at which it spoils. Now, an alternate way that I could speed up the rate of reaction if I didn't want to change the temperature of the system would be instead to provide an alternate pathway by which that ball might move from point B down to point A. And that would be kind of akin to like taking like a bulldozer to the hill. If you take a bulldozer to the hill, it no longer requires as much energy to get up and over that barrier to the reaction proceeding. Another way of stating that is we've just now lowered the activation energy barrier. And as such, more of these still lower energy collisions would now get over the hill towards the product side. And a way that we might think about doing that process in terms of providing an alternate pathway with lower potential energy would be, again, that introduction of the catalyst. So let's take as an example here the term in which we're going to use here the heterogeneous catalyzation for the reaction in which ethene, which is C2H4, reacts to hydrogen gas to form ethane, that is C2H6. A lot of these heterogeneous catalysis reactions are going to occur in places like, say, inside of an internal combustion engine, where we have a solid state catalyst like maybe platinum present that would speed up a rate of reaction there. Now, let's give a method by which this might actually occur. If the reaction between the ethene and the hydrogen is to proceed, we have to have a collision take place with sufficient energy to get up and over the activation energy barrier. But if I introduce a solid-state catalyst, some metal perhaps like platinum, we might see an event take place in which initially the ethene, the C2H4, initially undergoes a process we call adsorption. That process of absorption is essentially going to mean it's going to bond itself to the surface of the catalyst. Once it bonds to the surface of the catalyst, the hydrogen can also itself bond to the surface of the catalyst as well, and in doing so, those hydrogen molecules get split apart into individual hydrogen atoms, which themselves can then migrate along the surface of that solid phase metal. Now, as they migrate, they can then find themselves in positions where they can then react to the ethene molecule, and in doing so, as they form new bonds between the carbons and the hydrogens, the bonds between the carbons and the metal themselves would therefore be broken, re-releasing that species now in the form of C2H6. So essentially, after the migration and the chemical reaction takes place on the surface, the products then escape off the surface. And in doing so, all of those pathways are essentially facilitated by the platinum, but the platinum never actually is consumed in the course of that reaction. So long story short, that new pathway essentially requires a lower activation energy barrier, and therefore the rate of reaction could be sped up. Now, interestingly here, and the kind of key idea is, the rate of reaction in this case is pretty much determined not by the concentration of my reactants, but really by the available surface area upon which those reactants can then react to one another. So really what that tells me is no matter how much C2H4 and H2 I've got in the environment around there, my rate of reaction is really just entirely dependent upon how much of it can fit on the surface at any given time. Which really means, therefore, many of these heterogeneous catalyzation reactions really are not dependent upon the reactant species concentrations, and therefore many of them are zero-order reactions. So we've really provided here then a justification as to why a reaction may not depend upon the concentration of a species. All right. So that's pretty much it for your need for understanding catalysis at this particular point. That brings us to the conclusion of our discussion of integrated rate laws and half-lives. Thanks for listening. We'll see you on the next lecture.